Hi, my name is Melissa Mathers. I am a fourth-year undergraduate physics student, and my thesis project is using nanoparticles to increase the efficiency in solar cells. So currently, the solar industry is working really hard to make this technology a viable alternative to fossil fuels. And currently, we have the big problem that we need to make solar cells more efficient, and we need to make them cheaper before they can even compete. So if you think about the current market, we have 90% of technologies using some form of silicon wafer technology. And these technologies are only about 25% efficient in converting light into energy, and they are expensive to boot. They cost about 40% of the total cost of the solar cell, which is already expensive. So what we want to do is reduce that cost. So we have started to build things called thin film solar cells. So because the traditional crystalline silicon solar cell technologies are expensive, what we can do is actually reduce the thickness of the absorbing layer, the silicon layer, and make them into thin film solar cells. So they're about 100 times thinner, which makes them cheaper, but they're also less efficient. And so the efficiency problem is actually worsened. And if they're inefficient, then the cost advantage can even be offset in the long run anyway. So the question now becomes, how do we make the thin film solar cells more efficient? And scientists have come at this from a lot of different directions. You have seen scientists who texturize the surface of the silicon. Some scientists have tried using anti-reflective coating on top of the solar panel. And most important to my research is they've started to incorporate nanoparticles into the design. And so what that means is that we can use particles about 1/1000th of a meter in size, and we put them in various locations throughout the solar cell. In my design, we actually have the top glass layer, and then we put the nanoparticles underneath, and then you have your silicon absorbing layer, and the electrical connects underneath that. And using nanoparticles is helpful because when you have a nanoparticle that interacts with light, it exhibits something called surface plasmon resonance. And surface plasmon resonance is a property of metal and dielectric boundary. So where the metal nanoparticle meets the semiconducting layer, it's perfect conditions for these plasmons to exist. And a plasmon is basically an oscillation of the electrons in the metal. So picture you have a metal nanoparticle, and the surface electrons are able to oscillate up and down because they're just a cloud of electrons. And when you shine incident light, the frequency of the light actually gets the electrons to sync with it, and they start to oscillate at the same frequency as the incident light. At resonance frequency, that's why we call it surface plasmon resonance. Resonance is when this oscillation will be going at maximum amplitude. And at maximum amplitude, that's where we see the greatest field enhancement. And field enhancement is what's going to allow us to create a more efficient solar cell. And so plasmon resonance exists for a whole bunch of different metals that we can incorporate into our nanoparticle design. I use gold nanoparticles, they have a plasmon resonance right in one of the most intense wavelengths of light present in the solar spectrum. So the solar spectrum is really intense in the visible region, right around 400, 500 nanometers, and that's right where gold's plasmon resonance falls. Because we can get gold nanoparticles excited at wavelengths present in the solar spectrum, makes gold nanoparticles a perfect candidate for a nanoparticle enhancement in a solar cell. So once you choose the material that you want to use for your metal nanoparticles, like I said in my project, I use gold nanoparticles, you can actually shift their resonance even more than just based on what their physical properties tell you by changing the radius of your nanoparticles. You can shift the resonance of your nanoparticle even more by changing the size of your nanoparticle. So anywhere from about 40 nanometers to 400 nanometers, you'll start to see a shift in your plasmon resonance of about 100 nanometers in the wavelength. So what that means is that you can tune your nanoparticle resonance to be right at a frequency that is optimal for your design. And in the terms of solar, what we're going to look for, the optimal frequency is going to be one where we get optimal light to energy conversion. So for that, we have to look at the material properties of our absorber, which is silicon. Silicon, the properties that we know about it, we know the quantum efficiency, so we can measure. This is just a ratio of light going in to electrons coming out. It's called the quantum efficiency, and it's a function of wavelength. So at certain wavelengths, silicon is better at converting light to energy than at other wavelengths. So if we can get our surface plasmon resonance of our nanoparticles to be excited right at one of those optimal wavelengths, what we should see is our enhanced field at that wavelength and increased charge generation, which means better solar panel efficiency. So that's the physics behind my research, and I'll be doing a more technical talk at the You Will Discover Undergraduate Conference, Tuesday, March 24th, so I hope to see you there. Thank you so much.